Good evening to everyone. It is really a pleasure to have you with us today. My name is Nancy and I am the treasurer of the IEEE Women in Engineering Affinity Group of the student branch of Politecnico di Torino. Welcome to this special event, a special edition of the pitch involving Politecnico di Torino and Università Campus Biomedico of Rome. The event is called Bio-sPitch.D and involves the research teams of Joshua Di Tocco from Università Campus Biomedico and the research of Andrea Mongardi from Politecnico di Torino, both in the bioengineering field. At this purpose, I will invite for a brief presentation Simone Aiassa, chair of IEEE student branch of Politecnico Torino, and Riccardo Sabatini, webmaster of IEEE student branch of Università Campus Biomedico di Roma, to explain the aim of the branches. The Bio-sPitch.D was organized by the IEEE student branches of both universities with the support of the Italy section. And for this reason, with the immense pleasure, I welcome Professor Maresca of University Federico II di Napoli, which is the Student Activities and Educational Committee Coordinator of the IEEE section. And he will introduce himself and will explain his role in the IEEE Society. So I give the floor to Professor Maresca and then to Simone and Riccardo. Thank you.
Can you hear me? Can you see me?
Yes.
I think so. Thank you to all. Thank you for this invitation. Before to start, I would like to thank this organization. This is the first experience in which two student branches grouping together in order to share their idea of research and their results. This is the aim of the Student Activity and Education Committee Coordinator. Before I will start with my presentation, I would like to share this video with the president of IEEE section, Bernardo Tellini, in order to have his comment, his first comment, and also at the last of this conference, it is important to have also a comment by Tiziana Tambosso, that is chair of award in IEEE Italy section. Please, Bernardo, if you want to add some words.
Yes, thanks so much, Paolo. Really, thanks for this invitation and for the organization of the event. What I would like to say to you with really all our pleasure is the full support by the section on these initiatives. I think this can be one of a long series of next events that will involve more student branches, and this is one of the mission, the main mission of the section and our association to create a network. Those from our side, on behalf of the Italy section, I really thank you for this organization, and I'm sure for the success of the event, and best wishes and good luck. Thanks so much. Bye-bye.
Thanks, Bernardo. Now I would like to share my screen in order to present. Okay. Okay, I'm going to talk about a different perspective, how IEEE student and young professional can reach a relationship into IEEE Italy section. What I would like to do today is to provide you with a clear picture of what the student branch is in the IEEE Italy section, and now this important organization can contribute to the relationship with the activities both in Italy section and in all Region 8. The student branches are a forge of ideas, a training ground for experiences, often an activity scene of very varied local quality initiatives that are sometimes internationally recognized. There is an opportunity to transform this predominantly local activity linked to the historicity of research into a collaborative Renaissance workshop, into a network of knowledge in which and skill that can be useful in many respects. Meanwhile, I started from the last slide. Okay. Meanwhile, let me show you some analytics about student branches in our vision. The first one, some numbers that characterize the Italian specificity of the student branch can be seen in the images that follow. Meanwhile, IEEE is the largest organization of engineering in the world. It is divided into regions, and Region 8, of which Italy is part, with the Italy section, is the largest region. It goes from Groenlandia to Russia, and from Europe to Africa, including a part of the Middle East, therefore a very high potential. Within this territory, there is the Italian section, which expresses 40 chapters and 3 affinity groups, and together with this is a significant number of student branches. We will focus on the latter. In the year's vision, student branches tend to be an open innovation network, a Renaissance workshop in which people collaborate and cooperate to make ideas flow and transform them into innovations. Innovation is the application of the invention, and having a workshop in which the skills and knowledge acquired are often reused helps in the transformation of the invention into innovation. The network then amplifies this moment, sharing ideas, making them flow, extending them, and coagulating interest, experience, and projects. But let me show some numbers now. The numbers are interesting because no country in Europe has these numbers. The Italian students enrolled today at IEEE are 1,047. With a growing female participation that has reached 16%, with a distribution on all Italian institutions and research centers now reaching 75 among university, research center, and institution. A separate discussion in the type of engineering for which you participate in this association. The subdivision is roughly 1730. 17% is the class of classical engineering, and 30% the class of information communication technology, which is assuming an importance now. Small percentage for the other two areas, which are the one biological and the medical science and the physical, as promising for the future. But how many student branches are there? We have 21 student branches, 5 student branch chapter, and 2 student branch affinity group. But the participation of students is much more substantial because it covers, as I already said, all Italian university, as evidenced by the 3 snapshots on your right. You can see which show us that all Italian high-level educational institutions are involved. But what are the benefits and what are the costs? The benefits are many, ranging from the opportunity to participate in the contest and acquire awards, as this initiative, for example, to the opportunity to use free services such as free mailboxes, IEEE Resume Lab, IEEE Magazine, being able to read magazines and newsletters, and have student travel grants for PhD students, and doctor research. Discount on IEEE Congress registration, and much more. But at what cost? The cost is a pizza and a beer a year, of course. Indeed, $27 are today around 22 euros, but a special 50% discount if you sign up or renew next year is just to indicate the future 50 discount code when renewing and or registering. So this is an opportunity, an important opportunity that decrease the cost from 22 euros in 11 euros. Very few costs. This is the table of costs in 2020 IEEE membership dues. Let me say something about the future. We say that student branch has a huge potential to coagulate other forces, and this is happening in 2 events that we have already held 2 years ago in Como, and this one with in streaming with the Swiss friends. Particularly, the Pitch Competition Institute was enormously successful because a competition in that student branch, a young professional, shows the year research in 5 minutes video, really liked to people. So much that more than double the number of scheduled intervention arrived. That the network is that sign that the network is a powerful acceleration in dissemination of the knowledge. We intend to propose this pitch competition in an extended key next year at regionate level. So this is an opportunity for student branches and young professionals who would like to share their idea and their research idea, naturally. But there are 3 other important points worthy of attention that can make a contribution to this event today, namely the synergy with the industry. The first is a focus point of existing activities of the student community, because synergies and new projects can arise from it, which can see more student branches involved. Today's conference is an example of synergy, in my opinion, because two student branches working together in order to reach milestones. Another important activity that student branches are coping now is the one to involve much more companies. Much more companies. I am referring to those of information communication technology, but also the company in the medical sector are interested in this network, this huge network, because the network can be extended to all the region 8. And there are the activity to which IEEE is very sensitive at the global level, and those that the student branch involved in internationalization project toward the strategical and ethical activities. In short, also activity in common with WEAR could enrich this network in order to improve the way in which the idea flow and amplify the project and other idea. In short, what I'm thinking for the conclusion? Goals for next year could be, first one, improving cooperation. The network is now there and exists, also thanks to the support of young professionals with whom we have a fusion of intent while maintaining the very nuanced difference of the categories. We can improve this network, amplify the network. We would like to increase the number of subscribers in the student branch activities, and the discount could be an opportunity, but also some rumors tell me that things should go well if I look at my student branches. In Federico II, we will go from 27 to 40 members this year. The other goal is, and finally, the last goal is communicate. Finally, is disseminate my idea, your idea. This is an activity that we, as Italians, don't know how to do well, but we should do it professionally. Knowing how to do is important, but letting people know is one of the activities of research. Don't forget to remember this. And we must work well on it. IEEE provides us with news, letters, magazines, and more to do it. And we should take advantage of these opportunities. Otherwise, what we do remain relegated to the province of Region 8. I would like to conclude my presentation showing you contact and links of formal and informal tools where you can find the news and network, and you can participate to this network in order to improve and enable flowing of your idea, your research, and improve participation in order to acquire new project and new idea. Thanks a lot for your attention, and I give you the control.
Thank you. Thank you to Professor Maresca for the presentation, and thanks to Professor Tellini for the introduction. It was a pleasure to have you here with us, so thank you so much. Now it's the turn of Simone, Chair of the Student Branch of Politecnico di Torino.
Thank you, Nancy. Thank you, Professor Maresca, and also thank you, Professor Tellini. I'm the chair of the IEEE student branch of Politecnico di Torino, and I was thinking to say something like that is a pleasure to host you here, but I don't think that this is our home. I mean, this is the home of everyone. It's nice that in this unfortunate historical moment, we can, in any case, be together. And I'm really happy, I'm so happy that today we are demonstrating that two student branch from two Italian university, separate each other from around 650 kilometers, can share an activity like this. I cannot express how much I'm happy to see this happening, and I'm sure that in the future we will work more in this direction. Today, you will see one student from our university who will present his research that he has done in his master thesis. But I want to share with you that our student branch is trying to covering on a wide band all the topics related to IEEE in general. And as an example, we are dealing with emerging technologies, communication technologies, computer science, and so on. In doing this, we are presenting numerous free events on our YouTube channel. And so please, if you are following by YouTube, hit the subscribe button, or in any case, try to reach us on our social to keep updated on our events. And you can find all the link in the description. And so again, thank you everyone for being here. And I leave the floor to the other speakers. Thank you.
Thank you, Simone, for your words. And now it's time for Riccardo, the webmaster of Università Campo Biomedico.
Okay, so thank you, Nancy, for the floor. Good afternoon, everyone. First of all, I want to thank Professors Lini and Maresca for the introduction to the event. You have been really kind to find some time in your busy schedule to participate in the joint webinar today. Thank you. Thank you also to Professor Tambosso and Schina for the support in the organization of this event. You were fundamental for the achievement of this broad audience. Thank you to be with us today. Then I want to spend a few words on this collaboration with the fellows of Politos. Perhaps to say that I am happy to have found such a proactive group to work within the organization of an event of this magnitude. Maybe limiting and showing the esteem I have found for a group as close-knit as that of the student branch of Turin. This event was created with the aim of giving students the opportunity to approach the world of research, breaking down the wall that divides the students from the researchers. The link between these two words can only be the PhD students, students with the key of the world of research. The pandemic has reinforced this wall, driving the students farther and farther away from research, excluding them from the university life, and almost all opportunities to do research. Making a virtue of necessity, guided by the mutual esteem and similar events, we created the first joint event, the first of what I hope will be a lasting collaboration in coming years. We, the student branches, as Open Innovation Network, have the duty to collaborate in order to produce events like this. I'd like to take this opportunity to thank all the organizations that supported us in the organization and dissemination of this event, as IEEE Italy Section, IEEE Sensor Council Italy Chapter, IEEE AMB Italy Chapter, IEEE Young Professional Affinity Group Italy, ingegneria-biomedica.org. Thank you very much for your work. Finally, before leaving the floor to the pitchers, I want to congratulate both of them for the importance of their work in the biomedical engineering landscape, the innovativeness of the work itself, and wish them a bright future in the biomedical world. So now I give the floor back to Nancy. Thank you all.
Thank you, Riccardo. Thanks for the contributions of our IEEE members, and thanks to the precious contribution of Professor Maresca. Thank you again. Before starting with the event, I would like to invite our YouTube followers and our social media channels followers to intervene with questions and curiosities that will be read at the end of the event. Thank you. And now it's time to start with Joshua research presentation. So to the presentation. Thank you.
Okay, thank you for the presentation. I'll share my screen. Can you see the screen? Okay, so I'm Giuseppe Tocco. I'm from the Unit of Measurement and Biomedical Instrumentation at Campus Biomedico di Roma. And today we'll present you smart textiles, which are devoted for respiratory rate monitoring and joint movement monitoring. So first of all, I would just like to highlight the talk layout. We will be focusing our attention on wearable systems, on the sensing elements that we used to instrument certain textiles to obtain wearable systems, how we developed these two systems for monitoring both the respiratory activity and the joint movements, the experimental tests that we performed, and then the final conclusions. So first of all, maybe all of you are aware that wearable systems are gaining more and more interest on the market. In fact, they are mainly used to monitor, let's say, physiological parameters, but mostly three main parameters, which are the heart rate, which represents the heart activity, the respiratory rate, and the physical activity. These wearable systems have they have three main requirements, which is comfortability. In fact, these systems, since they are wearables, they have to be worn for many hours during the day to provide the physiological data. They also have to be non-invasive, so in conjunction with the comfortability, and also they have to be reliable. So they have to provide the right information regarding these physiological parameters. Wearable systems are gaining, let's say, space in the use both in the sports scenario and also in clinical purposes for rehabilitation purposes. Starting from the sport activities, they can be used to monitor the performance of the athletes and also to prevent injuries and to provide informations regarding how physiological processes are involved in the sport activity that the athlete is performing. In the clinical purpose, instead, they can be used to assess the rehabilitation process, so to give a quantification of the progress that the patient is having during the rehabilitation process. So today we'll be focusing our attention on piezoresistive sensors. These sensors are essentially textiles. They are fabric that can be made of different, say with different technologies. They can be knitted conductive fabric where conductive wires are used to create an entire textile or entire fabric, which then can be used to develop different sensors, or coated fabric where there is a textile fabric, which is then coated with a conductive material, or we can depose graphene nanoparticles on a substrate. The sensing elements that we'll be focusing our attention today are the coated fabric, which we'll be referring to as type A, which it will be used for the monitoring of the joint movements, and the deposed graphene nanoparticles, which will be called type B, and will be used for monitoring the respiratory activity. Both these sensors have the same principle of work. Essentially, when these sensors have an initial resistance R, that when the sensor undergoes strain, a variation of resistance takes place. As we can see on the plot on the right side, we have a proportional variation of the resistance due to the applied strain. So these sensors, starting from the coated fabric, which will be used as the sensor for the joint monitoring, we cut the sensor shape in a rectangular shape from a commercial conductive fabric, which was an A4 sheet in dimensions of 120 millimeters by 12 millimeters. This sensor has been then provided with automatic buttons, which have function that is both for connecting the sensor to the surface or to the support, and also to provide electrical contact with the electronics. We then prepared a two-layer polymer encapsulation using the EcoFlex 30, and after waiting 4 hours for each layer for the polymer to cure, we obtained the sensing element. That is the final element that we'll be using. Instead, the other sensor that we'll be talking about, which will be used in the respiratory monitoring, is the sensors made by the deposition of graphene nanoparticles. And these sensors has been developed in collaboration with Sapienza University of Rome. So we started with the graphene nanoparticles, which have been exfoliated in liquid phase using sonication, and then we evaporated the solvent. We then added the carbon filler to obtain a conductive compound, which then has been mixed mechanically, obtaining the conductive ink. Then, using a screen printing technique, a sensor of dimensions 40 millimeters by 20 millimeters has been deposed onto a substrate, obtaining, after a curing at 150 degrees Celsius for 3 minutes in the oven, the final sensor. So first of all, we needed to understand how these sensors and if these sensors can be used for our applications, which are both the monitoring of the joint movements and the respiratory activity. So we decided to perform the metrological characterization using a testing machine that allowed us to set the amount of displacement to the sensing element, to set the speed to displace the sensing element, and to record the different parameters that we set during each trial. To collect the response to these displacements, we used a voltage divider and a NEDAC 6002, which is commercial data acquisition board, which has been used to both power the electronics and to collect the output of the signal. And this data has been collected in LabVIEW in a custom VI instrument. So starting from the characterization, we performed two different trials. The first trial was the static trial, which was used to evaluate one important parameter for sensors, which is the sensitivity. So how much they vary their output for a given input, which is in this case the displacement. And we did 4 static trials at a speed of 2 millimeters per minute with different values of strain. For type A, we used the 20% of strain because this sensor is going to be used for joint monitoring. Instead, for the respiratory signal, we used the 5% deformation. We did 4 static trials. From these trials, we obtained the average sensitivity in the entire range of measurement, and this allowed us also to obtain the calibration curve using the best fitting polynomial, which you can see on the left side. We have the black trend, which represents the mean curve, so the average curve between all the trials, and the shaded area represents the expanded uncertainty. Instead, for the hysteresis trials, we wanted to evaluate the output of how the output of the signal of the sensor was influenced by cyclical movements. And this has been made by simulating both the respiratory activity by using the same amount of deformation we used in the static trial, so 5% deformation, and simulating a respiratory activity of 12, 24, and 36 breaths per minute, which is corresponding to a speed of 0.8, 1.6, and 2.4 millimeters per minute, respectively, and also to simulate the elbow movements, which are represented by the speeds of 50, 200, and 600 millimeters per minute. From the data we acquired, we analyzed each trial, and we evaluated the maximum hysteresis error, which is shown in the equation in the bottom right side, where we can see that for each hysteresis cycle, which is shown on the left side in the plot, we calculated the Umax, which is the ratio between Umax and R0. Umax is the maximum difference between the loading and unloading part of the cycle. We obtained the maximum value of this and divided by the maximum value of the entire signal, which is the R0, which you can see is represented by the red dot on the left trend. So from these two analyses of both the type A sensor and the type B sensors, we obtained for type A a sensitivity of 0.03 volts per percentage of strain, and for the type B, 0.13 volts per percentage of strain. From the hysteresis trials, instead, we obtained the maximum hysteresis error, which we can see that for type A are a bit higher compared to the type B, but both showed good performances, and so that they can be used for the devoted applications. So then, starting from the joint monitoring, we decided to use an elbow guard, which was being provided with 2 conductive buttons. to which two electrical cables were connected, and these were sewed onto the elbow guard. These buttons are both used for fixing the sensor and also to provide the electrical connectivity to the electronic boards. The electronic board was essentially a voltage divider connected to a commercial MCU unit, which is the M56C, which was used both to power the entire electronics and collect the output of the sensor. And as you can see, this is the how the elbow guard has been worn, and we can see the output of the sensor on the right side. From this trend, we were able to understand that the ascending part, and to identify the elbow extension in the ascending part of the trend, and the descending part of the trend represented the elbow flexion. So we decided to test this system with a reference instrument, which is the Qualisys motion tracking system, which is essentially the use of 10 IR cameras, which record the 3D trace of 24 reflective markers, which have been placed on the arm of one healthy subject. The protocol we followed was to perform 10 elbow flexion extensions at 4 different speeds, 60, 50, 40, and 30 beats per minute. And to obtain this speed, we used a metronome. So we performed 2 analyses. From a qualitative point of view, we were able to assess that the wearable system is able to track the elbow movement, as you can see from the left trends, where the black trend represents the output of the wearable system and the reference system is the red one. So we can see that they are almost overlapping, highlighting as we stated before. And from a quantitative point of view, we were able to compare the systems in the count of each movement, and we were able to count in both systems the same number of movements. So both from a qualitative and quantitative point of view, this wearable system is able to track the movements of the elbow joint. Moving on to the respiratory monitoring. So we used the sensor that has been deposed onto a substrate, which is the graphene nanoparticle sensor. And in this case, the ascending part of the collected trend represents the inspiratory phase. So the deformation in this case is not provided by the joint, but it's provided by the expansion of the rib cage due to the respiratory activity. And the descending part of the trend represents the expiratory activity, so the compression of the rib cage. These sensors have been screen printed onto a running shirt, and after a polymerization of 150 degrees Celsius for 3 minutes, we obtained the shirt that you see on the right side. We then use conductive yarns, which have been sewed on top of the sensor, and they have been used to connect the sensors to electronic board. The electronic board consists of 4 Wheatstone bridges, which is a particular circuit which is able to transduce the variation of resistance of the sensing element into a variation of voltage. Then we use 2 instrumentation amplifiers to amplify the signal, an ADC, a 12-bit ADC to digitize the signal, 1 IMU, and 1 SD card for storing the data. We tested this system on 3 amateur athletes in a non-competitive race of 10 kilometers, which is the Atletico Milan Rome, which is performed in the center of Rome. And we monitored 2 types of parameters, the respiratory parameters and the race parameters. From the race parameters, which you can see on the top slide, on the top part of the slide, we were able to estimate the distance that the runner did during the entire race, the exercise time, and the mean pace. Instead, from the respiratory parameters, we were able to obtain the mean respiratory rate, which was equal to 50 breaths per minute, and the total number of breaths, which it was during the entire trial of 3,243. As you can see on the left side, both the respiratory activity has been monitored on windows of 30 seconds. So summing up, we were able to develop 2 systems that were fit for our purposes, but we are looking forward to use these systems for evaluating the elbow angles. So use a reference instrument to, let's say, calibrate the system and evaluate also the angles to enable to use these technologies from a clinical point of view, but also to provide indexes for the clinicians, which could be, for example, the timing of the movement, which could be used as a parameter that indicates the improvement of the patient during the rehabilitation process. Instead, for the respiratory device, we want to test this on a larger population using our reference system in order to validate the system for the respiratory activity, and also to perform a breath-by-breath respiratory analysis, so that this could also be used in a clinical scenario, not only in a sports scenario, to enable the clinicians to understand how the rehabilitation process is going. I thank you so much for your attention, and if there's any questions, I'm open for questions.
Thank you, Joshua, for your research explanation. A very interesting talk and very actual in this particular moment for worldwide health. So thank you so much. Now it's time for Andrea Mongardi, and then we will dedicate a space for questions and curiosities. So we can start, Andrea.
Thank you, Nancy, for your presentation. And thank you all to be here, even if virtually. So I will share my screen. And today we present you work in the medical system for gesture recognition with SEMG signal acquisition. So gesture recognition in this specific case is for hand gesture, so with forearm muscles involved. Gesture recognition can be applied to different scenarios, so robotic arm control, prosthesis, like vehicles, or many different applications. In this specific case, in the biomedical field, the most used approach is to acquire surface electromyographic signal from the skin of a limb. So in this case, from the skin of the forearm. And the SEMG signal is a signal that represents the musculoskeletal activity. Is a spare signal, so it stays on the average when it's not activated. And is the summation of near activities, because from the skin it takes signals of more than one single muscle. So the main advantages are that the electrodes are easy to apply, and the approach is not invasive because nothing is in the limb but only on the skin. There are also some disadvantages, of course, that they are addressed in this work. So the main one is the high field extraction effort of sampling the whole raw signal. And the another one problem could be the crosstalk between different muscles, the unwanted crosstalk, of course. So to address the high field extraction effort, my group in Politecnico developed a particular technique called average threshold crossing, or ATC. In practice, the threshold comparator is used to sample the signal in a different manner. So we can see here that with standard sampling frequency, we should have a lot of packets with more bytes for each packet in blue here. And with our approach, a TC signal, a threshold crossing signal, will be generated only when the SEMG signal crosses the threshold, so only when it's active and some movement have been performed. The pros, of course, are there are less data to transmit in wireless applications, or low power of the transmission, and no analog to digital converter is needed, so the device area will be lower, and we will see it in a minute. The ATC parameter will be calculated as the number of events, the number of spikes that are generated in a defined window, time window, that in our case is under 30 milliseconds. So this is the parameter. And the main problem is how to set a proper threshold, because a too high threshold would mean too few events or no events at all generated. And a too low threshold will mean activation even if the end is not moving, so unwanted spike. So the threshold in this case has been implemented a software routine. Threshold is set above the average of the signal, and then continues lowered till one or more events are generated, are found. If this condition is stable, then the threshold is raised of 30 milliwatt. That is the hysteresis of the comparator, and this is the final is our final solution in this case. So all the hysteresis of the comparator is above the signal, even if some noise is present on the arm, and that's a good solution for us. So no spikes when the end is in the rest position, and if the activation is small, you can always see spikes in a small time. So we can see the hardware solution for this approach. This is the two sides of one of our PCBs on one of our prototypes. And we can see that they're really small, so 22 millimeter wide and 25 millimeter long. And we can see there are a lot of components that are standard conditioning circuitry for SCMG acquisition. So all these components that I'm highlighting are for standard conditioning, all these ones. And we can see that for threshold crossing in hardware, as we have implemented, just a threshold comparator here and a digital to analog converter there for the threshold establishment. These channels are then inserted in a more complete system. So we have more than one acquisition channels on the form to acquire the SMG signal. So we have the form, the SMG signal here is analog. Then after the channels, we would have the digital signal. It is just easy to use with the microcontroller. We have an ARM Cortex M4F and some machine learning on it. In this case, an artificial neural network fully connected. So that we have the predicted class, and the predicted class is sent to a Zoom robot. So a small tank just for demonstration purposes that will perform movements. After that, we have to choose the gestures to be predicted. To control the robot on a planar surface, we have chosen the wrist extension, turning right, the wrist flexion for turning left, the radial deviation of the end to go forward, the ulnar deviation to go backward, the grasp, that is a special movement for special purposes. In this work is some music to entertain people during demonstration, and the idle position of the hand to stop the tank or to do nothing if it is already stopped. So we have 6 movements, 5 active ones, and 1 that is the rest one. 6 movements to be classified from the neural network. So first trial with only 2 input features has been performed with 1 input on the flexor carpi radialis, so on the medial section of the forearm, and 1 on the extensor carpi ulnaris, so on the distal section of the forearm. But we can see that these are the 5 active gestures, and they are not all seeable from this graph. In particular, the radial deviation is just 2 points there, so it's not a good solution for this problem. Adding 1 input channels, we arrive here. So in this 3D space, we can see also for us, for humans, it's easy to see the definition of the space of these 6 movements. So also the classifier will be able to perform it and to do a good job. The 3rd channel is in the abductor pollicis longus, as we can see here. So we have 2 channels, 2 differential channels on the distal section of the forearm and 1 on the medial section. A reference electrode has been placed on a neutral, electrical neutral area on the back of the end to reference all the 3 channels together. So after that, we have the 3 input features. We would like to obtain the 6 output classes, and we did an optimization of the neural network. We said it's fully connected, so this is a schematic. And after the optimization, we obtained a good trade-off between complexity of the online algorithm and the accuracy is to have 2 hidden layers with 26 nodes each. After the definition of the classifier implementation, we passed to the training and the testing activities. So we enrolled 25 people to an in vivo study, 20 to the training phase, and 5 to the online system test. In the training phase, performed on MATLAB. There have been 5 sessions for each person. with only the 5 active movements because the idle one has been extracted on post-processing. And 100 windows, 100 ATC windows for each person, with 2,500 data for each person, and 50,000 data globally for the training phase. And in this phase, we only add the digital signal and the classifier, so no output of the classifier has been used. In the testing phase, we use the ARM Cortex-M4F, as I said before. 5 sessions each again for each person, but all the 6 movements because we want to classify also the idle one. And only 40 windows for this test with 1,200 data for each person. In this case, we had the signal, the classifier, and in real time online, we had an output to send to the tank, to our actuator. So for the training phase, we perform a per subject code log validation with 10 repetition and 10 different regularization coefficients tried. And the final lambda that we found to be the right regularization coefficient is 0.01. In the test phase, to improve the accuracy of our prediction, we perform a delay slot. So if T with who is the time window, the ATC time window, we neglect the first one, and we take the sequence ones only if the two consequent classes are the same. So if are the same, the class is taken. If they're not the same, the old value is maintained. This allows us to neglect glitches and to have a more robust classification and movement of the actuator. So the testing phase gave us some results on accuracy of the system. As we can see, we should have 1,000 here on this confusion, on the diagonal of the confusion matrix. We have it only on the idle state because it's the easiest to perform, but also the other are fine. The extension is almost 1,000, and the worst one is ulnar with 749, but there are good results for us. The accuracy, the average accuracy and the accuracy for each movement, we have accuracy, precision, recall, and F1 score with average accuracy of 96.34%. Also, latency has been calculated directly on the microcontroller. The Apollo 2 microcontroller, embedded timer has been used. And the calculation have been taken only 8.5 milliseconds for the neural network from the input to the output of the neural network. Adding this to the 2 acquisition windows of the delay slot, we obtain a final latency of the system of 268.5 milliseconds. That's suitable for online application. In fact, we will see in a minute in a short video that it's really responsive. So it's really fine for us. Then the power consumption, last but not least, and we can see multiple contribution from the 3 channels used and from the microcontroller for overall power consumption of 2.9 milliwatt. But the best of this slide is this current absorption graph. We can see that the current absorption is really coherent with the timing that we acquired before. So we can see that it's consuming more for 8.5 milliseconds, each 130 milliseconds. So it's really suited with the effective behavior of the microcontroller. So here is the video, assuming all the real active functioning of the work. We can see here the 3 acquisition channels. Okay, some problem with the video. Okay, the 3 acquisition channels, the MCU here with the Bluetooth for sending the data, the Zoom robot there, the table, the electroplasmid on my forearm, so the palmaris longus on the medial section, and the abductor pollicis longus on the distal one, as well as the extensor carpi ulnaris. The reference electrode is on the back of the end. And we can see here on the scope that we have the 3 CMG signal in the color ones and the CT signal in light blue. So we are already seeing that the SCMG signal is analog and the TC is digital. So after I move my hand here, the tank is moving really responsive. So you see right, left. There we can see different activation scope too. And for go forward, only the middle one, the most activated, and go backward. Okay, we stop it here. So concluding, we perform a classification with 96.34% of accuracy, with using only 3 acquisition channels and classifying 6 gestures, different gestures. An artificial neural network has been implemented on the Apollo 2 microcontroller, obtaining a system latency of only 268.5 milliseconds and an overall power consumption of 2.9 milliwatt. Future works will be to implement some approximate computing methods on the microcontroller to reduce power consumption and computational effort, varying the electrode number depending on the application. In fact, we are already working on it, and embedding the microcontroller on the same PCB that we saw at the beginning of this presentation to improve overall performance and get rid of wiring that are a lot noisy. Thank you for your attention, and we'll be glad to answer your question, if any.
Thank you, Andrea, for your presentation, and congratulations for your research studies. And now let's start with the section dedicated to questions for our speakers. So Joshua and Andrea, I invite you to turn on your microphones and your cameras. Okay, we can start with the first question for Joshua. Did you test other joints?
No, we didn't test other joints, but we are working on developing other systems for other joints, for example, for the wrist or the knee. And so we're looking forward to that, knowing that these sensors can be used for the elbow. We will be developing for different systems for different joints.
Okay. Let's go with another question for Andrea. How did you choose the neural network architecture?
Okay, so we chose the neural network because using that particular microcontroller, the ARM has the CMCIS library package that is really fast and low power for matrix computation. So the neural network is the straight implementation to perform the task. So it's really simple, and thanks to those libraries, it's really fast and lower power consumption doing it.
Okay, thank you. Now a question for both our speakers. So, which are the expected timescales in which your research activities can be employed in concrete clinical applications?
Okay. Well, of course, these technologies have to be validated. So we can say that in the next, I think, 2 or 3 years, probably there will be an improvement in, let's say, the optimization of the system. It can be validated using reference instruments, and then probably it could be potentially usable in clinical purposes. Maybe not in very detailed clinical reports, but it can be used for certain monitoring or certain parameters in the clinical, for the clinical aspects.
Okay, and for you, Andrea?
Yes, for us, it's more rehabilitation purposes. So the ATC technique is already used in some rehabilitation scenarios for home caring or something like that. And the gesture recognition has to be improved. So also for me, it's 2-3 years of work. We are improving the acquisition. So adding more channels will allow us to recognize more gesture and more fine gestures. So yes, then it should be applied to processes control with a long battery life with respect to the one present on the market today.
Okay, thank you. Let's proceed with another question for Joshua. Is it possible to use the respiration movement to obtain other medical quantities using indirect measurements? If you did, what's the precision?
Okay, good question. Monitoring the respiratory activity, so monitoring the deformation of the rib cage due to the respiratory activity, it is also, we can also extract informations on the heart activity, which let's say on the rib cage, there is also the pumping activity, the mechanical pumping activity of the heart, which let's say the mechanical displacements that the heart performs during the pumping activity can be seen on the surface of the body, and this is called, there's a technique which is called BCG, which is ballistocardiogram or ballistocardiography. They are mainly used with other type of sensors, which can be, for example, fiber break grading sensors, which are more sensitive than pulse-resistive sensors. That's why they can be used. But sticking with let's say the pulse-resistive sensors, monitoring this activity, so the mechanical activity of the rib cage, we can see the heart activity, so the heart rate, for example, but data have to be filtered in a certain way. So there has to be a pre-processing phase in order to see the heart activity. And also it is easier to see the heart activity during the apnea phases. So when the only contribution on the deformation of the rib cage is given by the heart rate and not by the mechanical movement of the rib cage, so from the inflation and exhalation of the lungs.
Okay, thank you. There are some questions from the internal call from professors.
Yes, if I can, I would ask a question to Andrea. Is there some plan to integrate the system also in non-clinical environments? For example, in industrial robotics for control of robotic arm or similar?
Yes, okay. At the moment, we are only using robotics like the vehicle, the small vehicle you saw before, just for demonstration purposes, because we mainly perform biomedical activities. But of course, the system is studied from the acquisition part. So we analyze and we optimize the SMG acquisition and the classifier. When you have the output of the classifier, you can use it for what you want. So if it's robotic arm or a prosthesis, it's not the real problem here.
Can I ask a question?
Yeah.
Yes, a question to Andrea Mongardi. A question and a curiosity, obviously. The use of wrist rotation and hand movement contemporarily is possible, and the impact on the model or neural network. I am curious for the answer.
Thank you for the question. Yes, it is possible to perform more movement together, but in fact we will classify it as a single added movement. So we have already added some movements that are in studying now, and it's not the rotation in fact, but it is possible to add it. Of course, we add some pinch grip, some other tasks to recognize, but yeah, the fact is that we need more input channels. So with the 3 channels that we saw in my talk today, it is not possible to go more forward than 6 or 7 gestures. With the possible configuration is an armband on the forum, so not this placement on different position, but all around a fixed position of the arm of the forum, and that should give us more gesture to be recognized. Yes. Thank you.
I have a question. May I ask?
Yeah.
Thank you. The question is for both speakers. And do you have any contact with companies or industry to develop your prototypes for that company or industry, or any idea to develop these devices in a spin-off of your research for a startup or something like that?
Okay. No, at the moment we don't have contacts with companies for the development of this system, but sure, this technology is promising, and in a market that is growing for the need of wearable systems to give a personalized therapy for the rehabilitation of patients, or to give remote monitoring, so give less load to the, let's say, hospitals, so people can monitor their state at home. This could be actually an improvement for both the technology, so the market, but also for the patients that they don't have to go to the hospital to. But yes, we are looking forward in collaborations with companies to develop the system and optimize the system, bring it to the higher TRL level.
Yeah, so the ATC technique is already improved in some hospitals as well. So mainly in Boston, we have a collaboration with a research hospital in Boston, and the gesture will be not at the moment for the gesture part, but of course will be work on it. And we have some contacts with some startups here in Italy for rehabilitation, functional electrical stimulation, and application like that.
Thank you.
May I ask another question, please? A question for both speakers. Would you recommend embarking on the doctoral pathway to students who are graduating? If so, why, and what characteristics do you need to have pursue this?
Okay, so the PhD I think is recommended for students which have interest, let's say a profound interest in what they're doing, because it enables to see actually what you see during the years in which you study. So during your master thesis or your bachelor degree, your master degree or your bachelor degree, you see in practice, you really see technically and very detailed what you studied in years, and if it's something that you like and you're really interested in, you should pursue the PhD in engineering for sure.
Yeah, for sure. It's a really interesting experience because it's different work in the research that in standard works outside the university. So, of course, if, as Joshua told us, if you are really interested in what you did in your courses, just stay here and do your research as you want.
Thank you. Now there is a question for both the speakers. What are the benefits of being part of IEEE community for a PhD student? Can you share some of them with us? Thank you.
Okay, of course, being a member of the IEEE is being a member of a large community of engineers of all around the world that we can see has, let's say, a work family. And of course, there are many opportunities which are promoted from the IEEE. And for example, conferences or workshops that really help to promote the work that we are doing during our research activities and spread all our work around the world. Know other people, have contacts. So it's a great community, and it's great being part of this community.
Yeah, of course, the main opportunity is the network that IEEE create and that put us in. So. Yeah.
Thank you. Now, a speaker says, I have a question for Andrea. Is there a way to optimize the values of the threshold of TC over the time looking for a dynamic rehabilitation scenario?
Yeah, of course, there is this possibilities. It has already been studied in the past, but no big advantages have been found. So for the moment, we will maintain a fixed threshold. As I told you at the beginning of the presentation, the threshold is set at the beginning of each session. So depending on muscle activity of each person, the threshold is set in a proper manner. It's not fixed, so it's not a value known before because a calibration phase is performed. But we are not changing it during the activity.
Thank you. Okay. There is a question for Joshua, the last question. Is it possible to use the system to identify respiratory failure and hence any presence of COVID?
Well, of course, the system could be used to monitor the respiratory activity. We performed some studies on monitoring the reliability of these sensors on detecting the respiratory activity, mainly focused on the respiratory rate, respiratory frequency. Of course, we can also evaluate other parameters such as respiratory volumes, which could give an information about the integrity of the respiratory system of the patient or of the subject. And of course, respiratory failure can be assessed with the system, but it needs to, let's say, an improvement in reliability, and also to try to associate that failure to actually the COVID. So if the only symptom is respiratory failure, it needs a long time study to understand what is the baseline of the respiratory activity and how it's changing during the period of monitoring. So it could be used for COVID detection, but it doesn't give the certainty that failure is given by COVID and not for another pathology, of course.
Okay, thank you. Now it's time for the certificate of appreciation. We would have liked to give them to you in person, but the opportunity will not be missing. It is currently a virtual certificate. Thanks also to Andrea for your contribution and Joshua for your contribution. I invite the Professor Maresca, Tellini, Tambosso and Schena to turn on their camera for a memory picture now. Thanks. Thanks. So special thanks for Professor Maresca for the contribution at this event, and also thanks to in Tambosso for the support in the events organization. So it is the time for thanks. First of all, I thank the IEEE student branch of Università Campus Biomedico for having worked with us, with the IEEE student branch of Politecnico, with great commitment. I hope this is the first of a series of IEEE events together. Indeed, thanks to the IEEE Italy section always ready to support our initiatives. And also thanks to Professor Tellini and Professor Scana. Thanks also to the other sponsors of the event, the IEEE Sensor Council, the IEEE Young Professionals Affinity Group, and ingegneriabiomedica.org. Thank you. Thanks to the student branch of Politecnico di Torino with the advisor Maurizio Martina for the dedication and the realization of the events and for the purpose of scientific dissemination. Thanks also the Women in Engineering Affinity Group with Sabrina Grassini for the passion with which they collaborate with the student branch. And now I want to say that this year overcome the limits and the limitations of our and we have all stayed close. So thanks. And now I would tell you, so we
Sorry, we had some issue with the connection from Nancy, and we lost her just a little bit at the ending. But I think that we all know that it was a big thank you to everyone. And again, I want to say thank you to all of you. And I see that someone already went out probably from this connection, but in any case, thank you. And I don't know if someone wants to say something, please turn on the microphone and the webcam. You are welcome.
I just want to thank you all for your work, to the Polito friends, and to Professor Maresca, Professor Tiziana Tambosso, Professor Tellini, Professor Scana for your participation in this call. I also great thanks to our speaker, to Andrea and to Joshua. Thank you for your time.
Just 2 words also from my side. I would like to thank you everybody for your cooperation in the organization of these events, and I hope that, as was already said, that will be the first of a series of these cooperating events with the student branch, young professional, and at the next. Bye-bye.
Thank you very much. Thank you very much.
I would like also to congratulate with the very interesting presentation and for the organization. Thanks. The section really thanks your event. It's our thank to you.
Just a few words. A compliment is the best way to cooperate, the one in which we group together 2 student branches, promote an idea, share the idea, and promote a project. I think is the best way to accelerate innovation and to share the idea in other student branch. I suppose your initiative could be could have a relevance, international relevance, and so many thanks to improve this new way to accelerate using a network of idea, an open innovation network. Thanks.
Okay, I'm here for the last goodbye. And I want to say that this year was difficult, and our commitment overcome the limitations and the limits of the pandemic. And we have all stayed closer thanks to science and technology. So finally, I would to thank our followers who have followed us even from distance. So now I would wish you a Merry Christmas, and we will see you at the next event. Bye.
Bye. Thank you.
Goodbye all. Thank you. Thank you.
Bye. Thank you.
Bye all.
Bye.
Bye bye. Thank you.
Bye bye.
Bye all.